All right, so as promised, here is the video for the second scenario that we didn't have time to go over in class today. My request to you is please, please, please do not watch this video until you have completed that question or that side of the paper, until you've completed it yourself. And I'll tell you why. If you just watch this video and you follow along with me and you write down the same things that I'm writing down, it's not going to mean as much to you. But if you try it yourself, even if you feel like you don't know how to do it, put something down, all right? And then it'll help you learn from your mistakes. Even if you feel like you don't really know where to start, just do something, make an attempt to answer every question. And then I promise the video will be better for you. It'll make more sense. You will learn more from it, and you'll do better on the quiz tomorrow. All right? Okay, so with that being said, let's get into this. Now, I'm assuming you've done this already, so I'm gonna move somewhat quickly. I will explain stuff though, of course. Okay, so same reaction as before: copper sulfate and aluminum. First step, since we're given all of our amounts in grams, and we can't put grams in our BCA table, our first step is to convert these grams to moles. And we're going to do that for our copper 2 sulfate and for our aluminum. So using my data table here, I can see that the empty beaker weighs 50 grams, and the beaker with the copper 2 sulfate in it is 68.4. So that is a difference of 18.4 grams. So that must be the mass of my copper 2 sulfate. So I'll say 18.4 grams equals some number of moles, because I'm looking for how many moles. Now, in order to figure that out, I'm going to have to know the mass of 1 mole of copper sulfate, and that is the molar mass. So to get the molar mass, I'm going to add 63.55 for my copper. I'm going to add 32.07 for my sulfur, and I'm going to add 4 16s for each of my 4 oxygens. Remember, oxygen has a mass of 16, or a molar mass of 16, I should say. When I add all that up, I get 159.62 grams. And remember, that's the mass of 1 mole. So that's how I'm going to write it down here. 159.62 grams equals 1 mole. All right, now we can look at these numbers and we can decide our answer here. Is this going to be more than 1 mole or less than 1 mole? Of course, this is going to be less than 1 mole because we have less than 159 grams. We only have 18 grams. So I know that I have to do some kind of a division here because it's proportional. So then the question is, do I divide my 18 by my 159 or vice versa? And since I want a number that is less than 1, I'm going to do my smaller number divided by my bigger number. So 18.4 divided by 159.62, and that will give me, let's check, 0.115 moles. And there's my answer there. Now, just to prove to you or explain to you how I knew to divide my smaller number by my bigger number, let's see what would happen if I divided the other way. If I did 159.62 divide by 18.4. Now I got 8.675. And if you write your setup like this, then you know as soon as you put that 8.675 there, you know that can't be right because you already decided that it has to be a number that's smaller than 1, right? So that's how we know that it should be the smaller number divided by the bigger number. That always gives me a number less than 1. So that's my answer, 0.115. Now I'll do the same thing for my aluminum. 26.98 grams is the mass of 1 mole. I get that from my periodic table. And in this case, I have 1.3 grams of aluminum. How many moles is that equal to? Now, once again, I can tell that I have less than 1 mole because I have less than 26.98 grams. So I'm going to divide, once again, the smaller number divided by the bigger number. And I got 0.0482. And that is the number of moles of aluminum that I have before my reaction happens. That's what 1.3 grams is. Sorry, hold on. I just need to check something. Okay, yeah, that should be good. Okay, so now I'll take my numbers from question number 1, and I will plug those into my BCA table. 0.115, that's the amount of copper sulfate that I have before the reaction happens, right? This is before the reaction happens. And I'm also starting with 0.0482 moles of aluminum. My next step is I need to decide what my limiting reactant is. So to easily figure out what my limiting reactant is, I'm going to take this number, my quantity of copper sulfate, and divide it by 3. And I'm going to take this number, my quantity of aluminum, and I'm going to divide it by 2. So my 0.115 divided by 3 gives me 0.038. And the answer to this other question, 0.0482 divided by 2, gives me 0.0241. So on the example on the front of this page, remember that it was copper sulfate that we ran out of first, and it was copper sulfate that was our limiting reactant. But in this case, since this number is smaller than this number, I know that aluminum is actually my limiting reactant. So I'll label it right away. Now to fill in the rest of my change row, I'll take this 0.0241 and I'm going to multiply it by each of the coefficients in my chemical equation. So that's the 3, the 2, the 1, right, the invisible 1, and the 3. So 0.0241 times 3 gets me 0.0723. And remember, I am using up reactant in order to make product, so that's how I know to put a minus sign right there. I will put my 0.0482 moles right here. Of course, since aluminum is my limiting reactant, that's how I know I'm going to use all of it. And if I forgot that for whatever reason, I can take my 0.241, multiply it by 2, right? And I get that number back. How much aluminum sulfate am I going to make? I'm going to end up making 0.0241 moles, and I will end up making 0.0723 moles of copper. Of course, I started with 0 moles of both of my products. And now this is just a subtraction problem and addition, right? So I'm going to run out of aluminum. That's my limiting reactant. I'll take my 0.115 minus 0.0723, and I get 0.0427 moles of copper sulfate left over. And of course, those numbers right there. Great. Question 3A. How many moles of copper 2 sulfate were consumed? Consumed means used up. So I'm interested in the change in the amount of copper sulfate during this reaction. And that's right there. 0.0723 moles. How many grams of copper should have been produced? That should word is really important because as you saw in your baking soda lab, sometimes the amount of product that should be produced or like that you would calculate could be produced, sometimes you make a different amount, right? And that could be for a variety of reasons. Maybe your product is impure. Maybe it has impurities in it. Maybe your reaction didn't finish, so you actually have less product than you thought you would, right? So there could be all kinds of reasons why your actual yield is not the same as your theoretical yield. Your theoretical yield is always given by your BCA table. And it's actually always given by the A row of your BCA table. This is how much product should have been made from the amount of reactant that you started with. All right, and so our answer here is 0.0723 moles. Wait a minute, this is asking for grams. So that's actually not the answer. This is an important first step. We have to recognize that this quantity is this quantity, right? That's the right amount of copper, but it's in the wrong unit. So I need to figure out how many grams is that many moles of copper. Now, luckily, I know that 1 mole of copper equals 63.55 grams. So I can tell right away that I'm going to have some number that is less than 63.55, but this time it might not be as obvious what math you need to do. Well, I want to show you something. Imagine for a second that instead of 0.0723 moles, I'll just put that over there. Imagine that instead imagine we had 2 moles. How would you do that math? How would you figure out how many grams are in 2 moles of copper? Of course, you would just multiply this number times 2. Okay, let's try something else. What if instead of 2 moles, what if we had 10 moles? How would you calculate that? Yeah, you would just do 63.55 times 10. Okay, so far it seems like if you just multiply the number of moles by 63.55, it'll work. Let's try it with a number that's smaller than 1 to see if this keeps working. How about 0.5? 0.5 is half of a mole. And so maybe the way that you would figure this out is you would take your calculator and you would punch in 63.55 divided by 2, because you know that 0.5 is half of 1. But instead of dividing by 2, couldn't you also multiply by 0.5? Try it on your calculator. 63.55 times 0.5. It's the same as dividing by 2. So now, let's stop pretending, and we'll come back to our real number, 0.0723 moles. I can just multiply that by 63.55. We just demonstrated that that works. So we'll go 63.55, multiply by 0.0723, and I got 4.59 grams. And there's my answer. All right, now remember, that is how much copper should have been produced, but for a variety of reasons, maybe we end up making a little bit less than that, or maybe a little bit more than that. Let's check. Okay, so from our data table, it seems pretty clear to me that if we have an empty beaker that weighs 50 grams and a beaker with copper in it weighs 53 grams, how much copper do we have? We have exactly 3 grams. So I actually only was able to recover 3.0 grams, or whoever collected this data was only able to collect 3 grams. All right, so then quick percent yield calculation. We can do 3.0 grams. That is our actual amount, right? Actually recovered from our data table, right? And we'll divide that by our possible. That is what should have been produced, our theoretical yield. And that we said was 4.59 0.59 grams. Divide those two numbers, then multiply by 100. And we got 65.4% yield. So not great yield. I think the front side was something like 82% yield. So the person who collected this data didn't do as good of a job with their lab. But as long as we're able to do all the math correctly, that's all that matters here. So there we go. There's our answers. I hope that this was helpful to you. I'm going to try to get this up before 5, like I said. I think that's all I have to say. Good luck on the quiz tomorrow.